I wanted to give you an example of a proof using the inner product and orthogonality of bases, or of vectors, pardon me. So let's say we have a basis for an inner product space V. This should say inner product space. Show that the zero vector is the only vector that is orthogonal to all the basis vectors. Okay, so let's suppose that we have a vector that is orthogonal to each of these basis vectors. So we're going to assume that W, some vector in V, is orthogonal to each of these, so each V sub I for I running from 1 to R. So what does orthogonal mean? Well, orthogonal means that when I take the inner product of the vectors, I get 0. So the inner product of W with each V sub I must be 0. Well, what else do we know in this problem? Well, we're given that the V1 out of VR form a basis for the inner product space. Well, if it's a basis, that means that every vector in the space can be written as a linear combination of the basis vectors. So, since we have a basis for V, there must be constants, C1 out to CR, such that the W is equal to C1 V1 plus C2 V2 out to CR VR. In other words, W is a linear combination of the basis vectors. All right, so we want to show that W is the zero vector. It says show that the only vector that's orthogonal to all of the basis vectors is the zero vector. Well, if I want to show that W is the zero vector, I need to show that each of these constants is 0. The way we're going to do this now is the only other thing we have to work with is that the inner product of W with each of the V sub i's is 0. So what we're going to do is we're going to take the inner product with W on both sides. So on the left-hand side, we have the inner product of W with itself. On the right-hand side, we've got the inner product of W with that linear combination of the basis vectors. Now we're going to rewrite the right-hand side here using the properties of the inner product, where we can break up the inner product over sums and pull constants out in front. So we have the inner product of W with itself is the C1 times the inner product of W with V1 all the way out to CR times the inner product with W with VR. Well, what did we say was true about each of these inner products? Well, W is assumed to be orthogonal to each of the basis vectors, so each of these inner products must be 0. And then, of course, when we have all those constants times zeros and added together, we get a bunch of zeros. So this says that the inner product of W with itself is 0. And now, using axiom 4 of inner product spaces, the only vector that when you take its inner product with itself that gives you 0 must be the 0 vector. So we get W is equal to the 0 vector.